Let me share my screen. Google Chrome.
That's not a good sign. Google Chrome sharing screen. You'll be using the app. Okay, good. Awesome.
Okay. So I'm going to, I prepared a small slide. So I'll be, switching between the slide and Colab and my Notion board. So let me just quickly start from the slide. And okay.
Wow, that'll be making me look bad here, but
So thank you for this opportunity, and Dr. Judy has raised the bar. What I can only do is to stand on the shoulders of giants. So let me start. So in the previous chapter, we built an end-to-end machine learning project, and our focus was mostly regression models, decision trees, random forest techniques. In this chapter, we are concerned about classification. Now, just a recap on regression that was heavily discussed during last week's meeting, so as to establish a similarity between regression problems and classification problems. So the similarity between regression and classification lies in numerical data. Both classification and regression makes use of numerical data, but the difference is for classification, the data is discrete. So for instance, let's say I'm predicting the positions in a class, and that's from 1 to 5. The numbers are discrete, but for regression, let's say I'm predicting the prices of houses in Cape Coast, Ghana, and I can have a price like $60,419.40. So the price is continuous; it's not discrete. So that's the difference between classification and regression. Also, for classification, it makes use of categorical data. So I can have strings and I can have discrete numerical data. So let me move on very quickly. The goal for this chapter is to build a model that can classify handwritten digits in the MNIST database. Okay. In this chapter, I'll be discussing about the MNIST database while talking about some epical points, reason why it was chosen for this classification task, how it was imported using the scikit library, and features of this database or data set. Further down the line, I will talk about the different classification tasks we have, and in order of importance, or in order of how they were mentioned in this book. We have the binary classification, we have the multi-class classification, multi-label classification, and we also have the multi-output classification. Also, I will talk about model evaluation, where I will discuss different performance metrics such as the confusion metrics. I will talk about precision. I'll talk about recall. I'll talk about the very famous ROC curve and the area under the ROC curve. So let me how I'm going to do this is I'm going to be switching between my PowerPoint presentation, the hands-on textbook, the Google Colab, and my Notion board, if there are things I need to clarify. Before moving to the textbook, let me give a brief intro as to why we're making use of the MNIST database. So the MNIST database is a real-world data, and it was collected from high school students and employees of the US Bureau. And it was also derived from the National Institute of Standards and Technology. So it's a good database for people who want to try learning techniques and pattern recognition methods on real-world data while spending minimal efforts pre-processing and formatting the data, as this has already been done before. In the previous chapter that we looked at, that's the end-to-end project, we spent so much time cleaning the data, but the MNIC database has already been cleaned for us. So we're just, performing the classification task using this data. Also, let me now go to database here. So the data set was downloaded using the fetch OpenML class, and specify the name of the database here with the version. You can also probably look at the database from the browser, and you see the MNIST using the openml.org website. And also for whenever you're importing data set using scikit library, it's the data set as dictionary. The last last meeting we had, we talked about properties of the scikit library, and where we mentioned consistency and defaults. So for consistency, the scikit library has dictionary. So this dictionary has key and values. So for instance, now, if you want to find the data, to see the data, you can click on, go to the MNIST data. Let me see if I run the code here.
It's there.
Okay, yeah, and you can see the array of the data. And also for target, you can get the target's name, the description. You see the data description and what have you. And this is the describing the data set, the key, the target key. And if you want to, now let's look at this arrays, the data and then the targets. So for the MNIST database is made up of 70,000 data points, and because it's already preprocessed for us, we have 60,000 test sets, trained set, and we have 10,000 test sets. And because this is an image classification task, the pixel is of the image is 28 by 28, and the way it is calculated is for each of the pixel, it contains 8 bits. So computers cannot process the image by itself, so it converts it to 8 bits and it represents a particular point. So let me come to this particular board. So for instance here, let me zoom my screen. Let's say this is an image here. So each of these points represents a feature. So now we have 20, it's 28 by 28, 28 pixel by 28 pixels. It's not really the size, it's different from the size, but this is just like a representation. So, and since we have 8 bits here, 8 bits, if you convert 8 bits to decimal, that's 256, because if it's 11111, that's 2 times 2 times 2 times 2, 2 raised to power 8, that's 256. So because we are dealing with decimal, not because we are dealing with decimal, not bit, we have to convert the binary, the 8 bits to decimal. So that's why we have all these points here. And this is how the image is represented. So all these points are features of the image. So let me go on quickly, and that is it here. So we in this particular code here, right? They've mentioned, so we reshaped this. Now this is the size, so we can see the size much more clearly here. So it won't look very big, and we are considering the first point. Yeah, and we have to turn off the axis here, so it won't show the probably the numbers on the x-axis and on the y-axis. So we have to turn off the axis here. So this is how 5 looks like. And when we also tried looking at the label, the label is also 5, but now it's a string. So we have to convert the string to a decimal, a number rather. And we have to make use of this uint8 because it converts from 0 to 255. So there are other features too. So if we come down here like this, there is U8, which is from 0 to 255. And because this is like the maximum that we're dealing with, so we don't need to probably use this U in 16 or U in 32. So we can just stick with the U in 8. And moving very quickly, since we are converting the string to numbers, then we can work with our database. And in this particular code here, we actually viewed, the code is written here. A second, let me see. Okay. See it here. So we actually plotted all the points. So we could actually see it here in the data, in the test set. Let me continue. Okay. So these are the digits. These are the digits from the MNIST database. So we divided it into train set and test set as usual. And we are, first of all, we are considering the binary classifier, right? And for the binary classifier, it just takes 2 points, yes or no. So in this particular case, this returns a false because this is a Boolean statement, y equals to 5 or y equals to y underscore text w equals to 5. So if this is true, it returns true here. If this is false, it returns false here. And we'll now employ our classifier. So the first classifier we are actually trying is the stochastic gradient descent classifier. And this classifier has the ability to handle very large data sets, and it works independently. So we define our random state here. So it doesn't change every time when we perform the operation. And we also tried the predict function. So it predicts these some digits that is 5 as true. We define some digits somewhere here. It predicts it as true, and looks like it gets it right. So let me go back to the slide and see if there are things that I should have mentioned but I didn't. Okay. And also I want to talk about the juxtaposition between attributes, labels, and features. So normally we have features and then we have labels, and all of these are called attributes. So the term is loosely used, and most of the time people actually get it confused. What is an attribute, what is a label, and what is a feature? So like I said, it is downloaded from openml.com. That's open science online platform for machine learning, and based on the 7 design principles: consistency, transformers, predictors, and all of that. So that is why we have that dictionary. So for all data sets that is gotten using the scikit-learn library, you can easily get the 7. You can easily you can easily describe the data set using all those key and value dictionary pair. Let me. Okay, so now the binary classifier. So it distinguishes between 2 classes. That's 5 or no 5. And normally for this MNIC database, it contains 10 classes. That's from 0 to 9, right? So we have to just pick just 5 alone because we are looking at using binary classifiers. And I've mentioned all of this. I've mentioned all of this. Let me just move to the next slide here. Okay, let me see this particular line. So for performance, which is one of the most crucial things in this chapter, so there are different ways of finding performance. There are actually different performance metrics. So let me start from here. Okay.
Toby.
Yeah.
Can I also add some stuff as you go, or you'd rather not to be interrupted?
No, yeah, please, you can add some stuff. I
Awesome.
gladly appreciate.
Thanks. So like one thing that I really liked, like in the first section, as Toby was describing that, so there are 7,000 numbers in this data sets, and each of those numbers, like for example, 1 or 3 or 5, whatever, each of them has like 784 features. And one thing that I really like about that is that those features are actual pixel values, as Toby said, and those pixel values are depicted in like if you're dealing with that in binary approach, those are like 8 little bits that each of them can get like 2 instances, like probably 0 or 1, and then that's why we can like 2 to the power of 8 is going to give us 784 features. So I think 256, that's the value that each pixel can get. And then the good thing about that 784 feature is that we can reshape it. Like instead of like dealing with like 700 something number, we can just reshape it in a matrix form, and that's how it will create an image eventually by numbers, basically. And that's like it's 28 by 28. That is our picture frame. That's gonna end up like 700 something features, and that's like really I think it's really cool. And because we're gonna deal with images, that's how to change the classifiers to an image eventually. This is like I think it's a very important step for us, like at least for me.
Yeah, thank you very much. Thank you, Amira. And let me move on to the performance measure. So cross-validation
Interrupt you,
is
Toby. This is going to
okay.
be super important, right? This is the meat of this chapter. At the end of this, you should be able to read a paper or listen to a presentation and be like, yeah, that's a terrible model, or that's a good model, okay? So remember last week, the measures, and Toby went through this, where he talked about the regression tasks, right? versus this classification task. So this idea, when you're predicting a number, if you're trying to predict a weight, right, you should use a regression technique. But if you're trying to say, am I black or white, then you're using a classification task. And so remember that those continuous variables, I'm just repeating because repetition is good, I think. But if you remember the metrics for measurements, it was the MAE, RMSE, for those numbers, those type of values we did last week. And today, Toby is going to teach us more about these metrics, which are going to be very important.
Thank you, Dr. GD. Now, the performance measure. So cross-validation is really one of the most interesting techniques that is being used in validating in performance measurements. And there are different techniques to this. Last week we mentioned the k-fold, and we also mentioned the train test split, which is always used. And that thing about cross-validation is that it helps in resampling of data whenever we have limited data. So I'm going to be talking about all of this stepwise. So in k-fold, let's say we have these data sets from 1 to 6. That's number one. The first thing we do is we pick a particular k. Let's say we choose 3 as our k, and then we divide our data sets into 3 different folds. You can see 1, 3, 2, 5, and 4, 6. And then we apply our model to these 3 folds, making sure that each of these folds appear as a test data set. So that's the whole idea about k-fold. Now, the problem with k-fold is most of the time it is said that our k should be at least 10 or 5. I don't know how true that is. I've not experimented with that yet. But books that online, they've been like, if you want a less biased model, you should make sure your k is 10. You should make sure your k is 5, something like that. And but applying just k-fold is not the best thing, because your each of these folds is not like a representation of the sample size. So for instance, now let's say fold 1, we can't find some of the important features that we should find. Let's say 5 in fold 1, something like that. I'm just giving an illustration. So this is where stratification comes in. So stratification allows us to process our data such that each of the fold is a good representation of the old data sets. And this is why we are now applying the stratified k-fold. Yeah. So let's go back to the textbook and implementing cross-validation. So now they are applying the stratified k-fold here. So each of the folds that we are forming is like a representation of the old data set, unlike k-fold where you can just get different folds. So finding so the first thing that they did was to clone. They did a deep copy of the model here. That's the SGD that we earlier used, and they specified the number of 3 folds. That's the split, and it's random, so it doesn't generate different random numbers anytime you run the code. And at the end of the day, they were able to get this as the accuracy. That's 0.9502 and all of that. So after using this, they now also tried the cross-val score function. And what this function does is that it returns the scores. So they tried the cross-val score function, and the scoring is accuracy, and then we add this. So in all of this, it is said that the accuracy is above 93%. Now this leads us to the base estimator. So we have to import the base estimator class. And what the base estimator class does, that it allows us to define our own model. So all models here, like SGD, HGD, random classifier, and all of that, they are formed from the base estimator model. So in our model here, what we did is we defined a method fit, a function fit, and also predict. And this predict function, it returns an array, just one column, yes, and everything is false, because 0 means false, and we are dealing with binary classification. That's 0 and 1. So it returns everything here as false. We now apply our cross-val score again on this false, everything here false, using our X train and this 5 that was defined earlier on, and making use of CVS3 and accuracy. So after doing this, the result was that the list was 90% accuracy, which is not true. And the reason why this is so is because we have more false classes. Is it called classes? we have more false images here than true. So for instance, let's say we have 40% false images and then we have 60% true images. So if we run the same model, that means we should get accuracy of 40%, which is not entirely true. So it is more of class bias, like the numbers of class of features that not features of images that we have for a particular class. So that's why we have 90% here. Now, confusion matrix tries to solve this.
About the can I say something about the base?
Yes, you can.
So I noticed that was what I used to build the transformer. It's sort of like to take the way I understand it, it's a very important class in skit-learn. It's basically how you can transform your own classes into like a skit-learn model of class that has fit, predict, and fit transform and all that, which is why he used it here in the cross-val score. It wouldn't have taken it normally. It won't have taken just a normal class. Well, unless you did use the base estimator, which sort of like, I'll explain doc typing. It'll basically help, the way I can explain is it'll basically help your own class and to transform it into the into a scikit-learn class, which I thought was really interesting because that's what they used to do the transformer before. Yeah. Sorry.
I don't want us to get too much into the weeds here. He does use that, whatever you're saying, Chima, showing another good example of how to, the behavior of coding in scikit-learn, how to create your pipelines, how to create this. But I think the point of this this exercise here, which Toby mentioned really, is to show you, look, created a model that predicted 5. Then you wrote any number predictor. So that's pretty random. It could be right because you're lucky, or it could be wrong because you're unlucky. And so in that case, if you think about it that way, then if you still get an accuracy of still 90s, right? So you're looking at those 3K-fold results, like the screen we have right now, the array, where you have 91%, 91%, and 91%. So if you have a model that's more than 90% and it's random, then me and you know that that's a wrong model. And so it's just telling you that using accuracy as the scoring function in this class can be misleading. You remember last time we were getting good performance, but then when we use the cross-validation, the performance really drops down, right? For the RMSE in the last chapter. So this is the same takeaway point here. So don't get too worried, like, oh man, I can't write this. This is just to tell you, like I said, this chapter is all about understanding the metrics. So it's saying if you're reporting to Judy, if I give you a classification task and you come back and say, this is the accuracy, it means nothing, because even randomness can bring that. And that's why moving to the confusion matrix helps you unpack this.
And I have one thing to add to this. Of those 7,000 numbers, those are not distributed, like those are, the prevalence of each number is not the same as the rest of them. So there may be like less 5s than 10, than 0s, or like more 3s than like 5s. So these are something to remember. So like we have 10 classes and like a random thing, as Judy said, like 1 out of 10 times can just pick it correctly because the prevalence of our, am I correct? So the MNIST is not, so the numbers are not distributed like
No,
evenly, right?
That's why if you say no 5, you get
Yes, and also because it's a binary classifier, so
yeah,
we have just 5 and the rest. So definitely 5 has to be smaller than the rest, because 1, 2, 3, 4, 5, 6, 7, 6, 7, 8, 9, they are like the whole of 90%. So in this particular code, we are calculating for false. So then it has a very high accuracy for false, because we have like 90 plus data sets here. So if we have, let's say, 40 as false, then it also have something close to 40. So that's like the whole idea here. But confusion matrix tries to solve this problem. And for classification task, we make use of confusion matrix, and for clustering, we use contingency table. And that's because for classification task, we have 5 or no 5, and then these labels are actually defined from the beginning. But if you are making use of clustering of contingency table for clustering, it might exchange 5 for no 5 and no 5 for 5. So we might not really know which one is no 5 and which one is 5. So we can't make use of confusion matrix for clustering analysis. So let me move quickly. So for confusion matrix, we are making use of this cross-val predict. And why? Because this cross-val predict actually returns the test variable. So unlike cross-val score that returns the scores if they're actually right or not, but with this, we get the actual variable that was predicted wrongly. So we can use it to draw our confusion table. Let me see if there are things here. Okay. So using confusion matrix for this particular problem, we have this is the result. Let me go to this slide and probably look for check the next screen. Okay, so this is the results for the confusion matrix, and we have the true positive, false negative, false positive, and true negative. So the true positive actually returns the number of instances which are relevant and which the model correctly predicted. So for instance, now let's say I'm predicting for 5. Or if for my test sets, if it checks the test sets and it's 5, it comes here and adds a 5 here. So that's the whole idea. For false negative, this supposed to be 5. False negative, negative is false. It's not true. So this is supposed to be 5. Let me try and remember this. It's a bit confusing.
I can help you here.
Okay.
So this is something that's well understood for medics. It's probably the one thing of machine learning that we never struggle with because we have to do this. I'm trying to look for annotation. Annotate. So this is the predicted class, right? Here. And this is the actual class. So let's say our number has 1, our predictions has, maybe our sample size had 5, 5, 6. You guys can see my bad handwriting, right?
Yes.
Okay. Yes. So someone is supposed to say it's not too bad, but anyway. So this is so let's say this is our sample size, okay? The actual class here. Then and we talk about this. Let's say because Toby is going to talk about this about the threshold here, and say that let's say this is predicted as 5, this is not predicted as not 5, right? Because it's a binary classifier. So this is predicted as 0, this is predicted as 0, this is predicted at 5, and this is predicted as 0. Okay, so this is predictions. So if you think about this, and we usually talk about this in the line of disease, then what you're saying is that the true positives, where the predicted and the actual class is the same, then it's this one and this one, right? So in this case, would have 2, correct? This is very basic, but you really have to understand this. Then this where the actual class is negative, but it was predicted to be positive. So let's do this line first. So the actual class is 5, but it was predicted to be something else. So in this case, it's this number here, right? So we'd have 1, okay? And because in total, we should have 3 numbers of 5, which the actual class of positive. Then let's look at the negative. So in negative, where it actually was, so I should have changed 1. So let me change this to 5, right? So it's 6, but it was predicted as 5. Then the false positive here is 1. And I usually don't cram it. I just remember what's the class and what's the actual class, and then fill my matrix. And then the true negatives, anything that's not 5, which is correctly predicted, it's 1, 2, 3. So if you add everything, should be 3 plus 4, which should be 7, and should have 7 numbers, 1, 2, 3, 4, 5, 6, 7. So that's how you come up with your confusion matrix, right? And then now when you look at precision, you're talking of how, how many times is your model correct? And so that means you take your true positive over the sum of your true positive and your false positive, okay? So you'd say 2 over 3. So in this case, my model is correct 66% of the time. Recall. Recall is your positive predictive value. It's saying, G, and I like the example of the shoplifter, because that's how you're going to remember this. It's saying, I don't care if I'm wrong that Judy is not shoplifting. I just want to make sure that I catch anyone who has potential for shoplifting. And so that's the recall. And so with the recall, then you're saying the total predicted over the existing relevant. That's the true positive value, I think. And so it has total positives over total negatives and over true negatives and false positives, I think. But anyway, the thing here you have to understand is how you use this, right? There's always the precision recall trade-off. And what happens is that you want to get to a point where you cannot have both. And so you have to decide. So for example, if you're building a movie to catch hate speech, you probably want to catch all possible terms that are hate speech and have a human being review them. Then that means you want a high recall. Catching is recall. But let's say in the example they give in the book, which is you want to make sure that the videos are safe. So you don't want to catch all possible videos for kids. You want to make sure that with 100% certainty that when my child watches this video, they're not gonna watch porn. And so in that case, you want to be very precise that you're correct most of the time. So you could flip that into, I want to make sure that I'm catching all the pornography videos. So if you're trying to catch everything, then you're talking about recall. And the thing that tries to get a balance between the precision and recall is the F1 score. Someone else can try and explain.
So one way that I think that this is, at least one part of the machine learning that I think my medical background helped me to understand is this thing, because this is, to me, I look at it as sensitivity and like positive predictive value and specificity, that those are the stuff that we usually like deal with. So we have disease, and so we usually like a medical area. So we have a test, and we're hoping that test correctly like if somebody is diseased, that test to diagnose that disease. So if we can diagnose the disease, that's going to give us like high precision and sensitivity, but they have like different names. So I thought the precision here is positive predictive value, meaning that out of all the positives, how much of those positives I am detecting out of those all porn videos, how much of them I am detecting. That's the precision to my understanding. And recall is sensitivity, meaning that out of all the healthy videos, kid-friendly videos, how much of those I am detecting. But in kid-friendly videos, obviously I want to like make sure that my precision is higher than my sensitivity, than the recall, because we don't care if we gather like 10,000 good kid-friendly images. What we want to make sure that is not happening is that out of those porn videos, 100% we diagnose them and not let them to come to our like collection or whatever we are using this test for, or like this model for. So that helped me. And then F1 scores, they had its own like definition. It's a harmonic mean, and I didn't know what that was, and I liked it to learn it over here.
Yeah, thank you. From now, I think I understand it now. And my thought process initially was that for recall, recall deals with like a particular label. So like the amount that was predicted right over the total number of existing relevant label, which is here. And for precision, it talks about the prediction. So this P here, so the true positive and the false positive over the true positive divided by the addition of these two. So let me go back to the
Also,
okay,
I think
so
you need to erase
clear.
Judy's annotations from the screen.
Okay, I think clear all drawings. Thank you. Okay. So from this particular confusion matrix, this value here 53,007, and this we are correctly predicted. This is the true positive and this is the true negative, and this were wrongly predicted, and it was explained here, and modeling like an actual scenario where we made a copy of these predictions here and used it to plot the confusion matrix. We had the zero value here and the zero value here. So this is the formula for precision, and this is the formula for recall. So from, let me see, it wasn't explained here. So now in this particular scenario, right, since we are predicting 5 for the precision, we predicted 3 5s here rightly, and then we had 1 here wrongly. So 3 divided by 4, and for the recall, we predicted 3 here rightly, and then this we are wrongly predicted as negative and we were positive. So that's 3 over 5.
Yeah.
Okay.
Mm-hmm.
And getting the precision score, this is the precision score, and this is the recall score. So from the precision score, we can say that compared to the previous 90% that we had when we made use of 5, we can say that 72% of the time when the model was drawn, we actually picked the 5. And then we can say also from here that when we are looking at just the 5%, the 5 labels in the data set, it detects 75% of the 5 labels in the data set. So that's the meaning of this. And then we also calculated the harmonic mean, which is the sum of the the average of the representations divided by the inverse. And the reason why we do this is because if you are using more mean, if you are using a normal mean, it gives the same weight to all the values. So also after calculating the harmonic mean, we then use it to calculate the F1 score. Let me see.
Yeah. Yeah. Keep going.
We then use it to calculate the F1 score. And now for the precision and recall trade-off, there is always a threshold here. So for instance, if the threshold is here and we are moving to the right, so when the threshold is here, that means for precision, we have 1, 2, 3, 4. 4 were correctly predicted, 1 was wrong. So we have 4 over 5. If we move to this place, it decreases again to 3. It increases rather over 3. So now the whole idea is when we increase our threshold, the precision increases and the recall decreases. But when we plotted the AUC curve, we saw that it's not in all cases that the precision always increase. So if we move this threshold from this point to this point here, we are going to have 3 over 4, which is lower than 80%, which is 75%. So it's not in all cases that increasing the threshold increases precision. But whenever we are increasing the threshold, we are always decreasing the recall. So we have to choose the threshold that we want to make use of in our prediction. So for instance, now for us to actually choose the threshold, there's a function known as this decision function that returns like the score, because it is the score that is always used to make these predictions, yes. So when we use we can get the decision function for a particular digit, and then we can also set a threshold here. So if the score is below the digit, then it predicts it as true. If it's above, it predicts it as false. So for instance, when it is above here, it's false. So for us to actually, I think they actually got their threshold here. So let me start from here. So now we now plotted the recall and the precision with respect to the threshold, and it was explained here also that when we increase the threshold, right, the recall always decrease, as we can see here, the recall. But if you look at it closely, we can see that it's not always constant. It's not like a steep slope that goes up. So precision will increase, but it's not in all cases that it increases. Like we saw earlier on here when we moved this particular one to this place, because when we move it from year to year, it becomes 3/4. That's 3 and 1 wrong 6. That's which is lower than this 80%, which is 75%. And moving down, then we plotted the precision and the recall.
So here I think was mainly like, when do you use a PR curve, which is precision recall curve, and when do you use the ROC curve, which is where you're going on to next?
So calculating the precision score, MC 90. So if we choose the score as 90, this is, if we choose the decision function as 90, the threshold, sorry, as 90, then this is our value for precision and this is our value for recall, because we know that when the precision increases, the recall decreases. And we need to know when to choose the appropriate or the best fit threshold in our data, in our analysis. Now we move over to the ROC curve. So this curve is somewhat similar to the precision recall curve, but instead of plotting precision versus recall, we plot the true positive, which is the recall, against the false positive rate. And when we do this, let me see the deadline. Okay, so yeah, we actually make use of the ROC curve here, and it returns them three different variables. That's the FER, the false positive rate, the true positive rate, and then the threshold. And when we plot the curve here, so this is the inference from the curve. So from this curve, we can see that the area under the curve, we can also calculate the area under the curve. So if the area under the curve equals to 1, that means the classifier is perfect, as we can see here. And going down, let me see, otherwise there is okay. So from here they said use the okay, let me see. So now the trade-off in making use of either the ROC or the precision recall curve. So as a rule, if you have more false positive, if you care about more false positive than the negative, then you can make use of the PR curve. Otherwise, you make use of the ROC curve, which was also stated here. And now training the random forest classifier to compare its ROC with the AUC.
Can I ask a question before we move too far? Going back at the top where it said 1 minus the specificity, why is that? Like, I didn't get that part. This one.
Okay, this.
Mm-hmm.
So there's a formula that's the FPR plus the TPR plus the TNR, which equals to 1.
Okay.
So
that's the first. Okay.
So the ROC curve on the y-axis is sensitivity. No, that's on the, so it's sensitivity versus 1 minus specificity.
Okay.
And I don't know why though, but I think it's just because it's also the same for, so if you look at it similar to, but instead of plotting the precision versus recall, the ROC curve plots the true positive, the TPR, which is also called recall, against false positive rate. And the false positive rate can be calculated by, so the false positive rate is the ratio of negative instances that are incorrectly classified as positive from that confusion matrix. So the 5s, no, the 6 and 7s, which were classified as 5. And so, and it's equals to 1 minus the true negative rate.
Okay.
It's
so
just,
is that why?
Yeah, Almira, I see you want to say something?
Yeah, like, again, like this is like the definition of a specificity. The true negative rate is a specificity. This is what it is. And like true positive rate is sensitivity. Those are like, and then then false positive rate, by definition, is going to be 1 minus true negative rate. That's basically, if you, I suggest, I'm not sure if, because I have learned this based on disease and like test to detect those diseases, that just makes sense. Or I'm not sure if I'm using the disease model because I've been learned this the whole thing on that, or is that something that maybe will be more easy, maybe like for Abby to like learn it, because the whole ROC curve can be explained with that, with sensitivity, specificity, positive, not the positive predictive value, but all of these it can be explained with a disease model and like the test that we are trying to detect that disease. And to me, that's like very good example. And then you can just, if you base your learning on that, then you can just apply that to change it, your mindset to like machine learning, like ROC definitions, which is basically the same.
Okay. So I was just trying to understand, like now that you've explained that, but when you look at the curve, you see there's that diagonal line and then that other line that's like on the left side, and they were talking about like on the left side. I don't know if that's what they were explaining about the ROC curve.
To the ROC curve.
Like you see that diagonal line and numbers more towards the left, you don't want it to come close to the diagonal line. Is that an indication of the true positives, or?
That diagonal line is what we have created there, showing that if our model was random, that's corresponding to like 50-50 chance. So we want that blue curve to be more to the left side of that diagonal line, and like include all of those area that we have plotted. The more, the better, basically. And that dotted line is basically there to like show us that what randomness is, and like how our model is distant from that random line toward the left and upper hand corner.
Okay, and that equals to true the TPR, right?
So TPR, so.
No, I'm saying, I know you said that this is like you want our the randomness is that line, and then everything else needs to be towards the left, right? So I'm just trying to get, okay, so if everything needs to be onto the left, then that means that's the side where we have our true positives.
It's a balance.
It's a balance.
Exactly.
It's a balance, because the more you increase one, the more you decrease the other.
Okay.
Right. So that's the like you can't have the perfect one would be 1, which would be like a line that goes up to 1 and flattens out. And so I find a good way to explain this. I get what you're asking, but I'm not so sure that I'm ready to explain it now.
Okay. Thank you.
Okay, so let me just add something to it. So basically, if this curve, if it comes like this, then that's when it is equals to 1. So since it's like this, it's close to 1. And since they said in the book that 0.5 is for a random classifier, so the goal is always to have like probably like something very close to 1. This looks good to me. So moving on quickly, now we are training and previously we made use of SGD, and now we are trying a random classifier to compare its ROC curve and the ROC AUC score. And for the previous SDG, there was another function that we used, we used the decision function, but this doesn't have. So to calculate the probability, we make use of the predict proba function method. And for the predict proba method, we include it here, and almost like the same thing that we did previously, 3 folds, random 42, and we define we make use of the instance of the forest classifier here. And when we do that, we also, let me see, calculate the ROC curve using the values for the scores and the scores forest that was defined here. So this particular function defines from 0 to 1, I think. But let me continue. Now we make our plots. So B, stands for blue and it's broken, and also for the black. And plots, making our plots like this, we can see from here that the ROC curve here and the AUC, this is the SDG here. I'm a bit confused here now. Let me
No,
just
no,
scroll up a bit.
you're right. Like, so it's just you have the label over there. Like,
Okay.
the SGD model is just the blue one, which is like doing worse, as we discussed before, than the random forest, which
Than
is
the
the
random
blue
forest.
one, which is more toward the left and up, meaning that it's having like a high precision and like high, not precision, but high sensitivity and also like high specificity.
Yeah, compared to the SGT that is a bit down here.
Mm-hmm.
So moving on, these are the scores for precision, and then for it's 6.6% for recall. Now for multi-class classification, now we've been dealing with just two binaries. I said two binary, just a binary 0 and 1. That's 5 and not 5. Now we are looking at probably how can we classify from 0 to 10. So there are two methods to this. We can either make use of the one versus the rest strategy or the one versus one strategy. And now how is this done? So for the one versus the rest strategy, we create different classifiers for 0, for 1, for 2, 2, 9. And then that's 0 on 0. That's for one classifier. For 1, 1 on 1, 2, 2 on 2, just like that. And at the end of the day, we select the best out of the classifiers, the one that has the highest scores. And we can easily get the scores now using the previous function that we talked about. That's the cross-val score, right? And another strategy that we can also employ is the one versus one strategy. And with this, we pick two of these data sets together, two points together, or two labels together. Let's say 0 and 1, 0 and 2, 1 and 3, 1 and 4, like that, and then we train. But in this case, we're going to have like more results, like more classes, because that's like a lot of iteration. So this is the formula to classify, to see how many classes I'll be getting at the end of the day. So when we use this, we can see that we will be getting like 45 binary classifiers. And after doing all of this, we now have to choose the best. So some algorithms like SVM actually allows you to call, it innately calls any of this strategy. So if you do not specify if you want one-to-one or one versus the rest, it innately calls any of this. But you can also specify, like we have here, we did not call any of the strategy here. We use the SVC classifier, and when it's predicted, then we now realize that it makes use of, what does it make use of? Let me see. It makes use of the one versus one strategy, but it wasn't explicitly called there. And how did we know this? By looking at the results. So we had like 10, and then choose the highest score. Now, specifying it by ourselves, that's one versus the rest classifier. And this is how we specify it, unlike the former one that we did not have something like this that required a function in it. We now put the SVC function inside this function, and after calling it, we realized that, let me see. So after using this particular one versus the rest, this is the results after training, yes. And let me see, decision function method. So we are now trying to compare the decision function for one value per class to that of the SDG classifier assigned to each class. So when we do that and put in this some digits here, which is 5, this is what we get. And then we calculated the cross-val score using accuracy. As we say, accuracy is not always the best metrics to use. Now for error analysis, yes, so let me just move quickly. For error analysis, so let me move to this particular place. So let's say we have a data set like this, and then there is, after plotting the confusion matrix, we have something like this, and we want to see if there are any errors in our data set. So we plot the confusion matrix, and we plot the confusion matrix with our column map as gray, and from here we can see that this middle definitely will be white, but when we look closely, we can see that from 5 looks a bit gray, which should not be so, which means that 5 was probably not predicted correctly. And one way we can actually solve this is by normalizing our data, and that's by dividing every row by the highest value here. So when we do that, it results to something like this, and this one becomes black because, as you know, 0 to 255, 0 is dark and 255 is white. So after this, we can now realize that 8 wasn't here previously, and now it's a bit white. And we can also see when we look closely to that for 3 and 5, 3 and 5 is not correctly classified. And one way we can do it is that we can now choose to plot these two values so we can see the mistake that probably that the classifier is making. And that was what was done here. So we plotted the 3 and then we plotted the 5. And then we can see that it looks somewhat similar, and that is why the classifier is actually confusing both of them. So this looks like it has a tail. It's not like 5, like an actual 5. It's a bit curvy.
It's a bad handwriting.
So, Toby, on that image, the number ones. So, so these are like plotting a figure. The left upper hand corner are all the 3s that are correctly classified as 3s, and then the right lower one, all the 5s that are correctly classified as 5s. So upper part, the 3s, those are the 3s that are, there were 3s, but they were classified as 5s, and we can see that those are like distorted. And like on the left lower part, those are the 5s that are misclassified as 3s. And that, so this is just trying to like show you, right? This is just trying to like show you, like visually, we can tell that, yeah, like left lower hand corner, yeah, these are 5, but our brain is like so smart, so it can easily classify this number, which is distorted for the our algorithm, as a 5, because we are so like good at this. Like, our brain is so good at this, but our algorithm cannot correctly classify it, and we can just see why, because those are distorted.
Yeah, thank you, Amira. And like she said, the left-hand side is the one that were correctly classified, and the right-hand side were wrongly classified. So we can see that this looks a lot better to me than looking at the same thing with the 5. The 5 in the on the right-hand side is a bit distorted. So probably that is why the classifier is actually misclassifying all of this. So doing something like this, we can actually, find errors in our data set and, try and correct them. And now for multi-label classification, we've been dealing with just one label, and that's probably true or false, one label. So that means a prediction cannot have more than one label. So for in this particular classification, we are dealing with more than one label. And how can we do it? So in this example, for instance, when we are looking at if the number is actually large, and if the number is also equals to 5. So after training, 5 is some digits here, 5 is less than all this, so it's false, and then 5 is 5, because 5 is we are predicting 5, so 5 is true here. So because the digit is 5 and we're trying to predict 5, some digit is 5. So that is why this is here. And also some classifier actually allows us to impute more than one label. So for instance here, using this multi-label, let me see, using the key-neighbor classifier allows us to actually make use of more than one label, as we can see here. So that's for the multi-label classification. And then going to multi-output classification. So multi-output classification is all about having more than one output. So let's say, for instance, now I'm trying to filter my image or clean my image or remove noise from my image. So the output is still like the same thing. It's not that I'm predicting just like a particular label. How can I explain this? But it's like I'm trying to clean the noise from the data. So that was what I got from reading this particular line. So for instance, now let's say this is the noise, and then I add the noise to my data here, the random noise, and this is the test to mode, adding the noise to my test and trying to plot it. So this is the one for test and this is one for train. And so when we try training and cleaning the noise, this is what we get. So
I think that he is like cheating here, and like he's cheating very good, because if you scroll up, so what he did, he's trying to like tell us that how to denoise an image using all of our algorithms, but he's just cheating. He's not really telling us how to denoise it. He's just adding some noise to our like train set, and like also to our test set. So here, like on the X train, underscore modified X train. So it's just adding noise, and that noise is just using like a NumPy array random function. So it's adding noise to that train set. Also, and like if you see, there's Y train modified Y train is actually the actual training set without noise. So here we're not, our labels are not the same labels. We have changed them. So our normal without noise images now is our label, and our train set with noise is our like input. So it's so he's using that to show us how they can use models. But I feel like I was actually going to ask you, do you, I'm sure we're going to learn it later on, but if you wanted to actually, without doing this cheating, what would you do for the noise and image?
Yeah. when I actually,
generative adversarial networks, like the old DeFi, right? You've seen those.
But that's like, we are adding something to our images. How can you just take that out? Maybe you can just take out some defined noises. Maybe we can use it for example, maybe we can, I'm just guessing, if we say like our modified training set is the current training set minus noise. Mm-hmm. And then we will use sorry, so that's going to be our output, like the Y train modification is our current train minus noise. And then we're going to feed it with our input. So maybe that, could that give us some noise reduction?
I don't know. But I know that people are using this for MRIs and CTs, like low noise to low dose CT scans to make them good quality. But I just haven't read how they do it.
Yeah, so basically this is like plus the noise, and we can just probably denoise it just with adding like minus noise, because, and I know that there are multiple noise patterns. So this is using one of the random noise pattern. It's like a np.random.random. So this is just a random noise added to the, where we can just take that random noise out of any image using the same functions that he's using over here. Mm-hmm. I guess so. And then one other thing that Toby, on the confusion matrices and the error matrix, and this one, I thought like the diagonal is actually the diagonal line is actually the correct predictions, right?
Yes.
And then the more white, meaning that we have either more correct prediction, or we have more of that particular number. So we have like 10 instances in each, like in that diagonal line, we have 10 instances, like from 0 to 9. And then probably like, if you scroll a little lower down, no, I just wanted to have that. Okay, so here, so the brighter, meaning that we have more number, right? We have more number 2s, and luckily those number 2s have been predicted as number 2. So that's why the second from the upper hand side, the second is whiter than for example 0, 1, because and then the most grayest one is the 5 in the center, like there, because first we have less 5s in those 7,000 instances that we have, images that we have less 5s to begin with, and some of those 5s has been misclassified also. So that's why we, like, compared to the rest of the numbers, we have like we have less values, and we have like as he discussed like a higher like in the upper sections, we have changed those numbers to pixel values. So the higher the number, the whiter the pixel value in the confusion matrix.
Yes, thank you, Amira. I also love to add So prediction is predicted is
The column.
horizontal and actual is vertical. So here is actual, here is predicted. So
Yeah,
for 0 to 9, 0 to 9. So that's why if it's 0 and it's predicted as rightly, then the
exactly.
number is very high.
Yeah.
And if you look at this, if you look at the 2221898, you can see that that's an outlier, right? If you look at the second last column here, right? So you have 5, 5, 7, 8, 0, 22, 7, 8, 45, 35, 5, then 2, 2, 2, right? You guys see it?
It's like,
Yes, I
yeah,
can
it's
see.
just more dispersed there. Exactly.
Yeah.
And so so that's like the 8, right? And then lots of the numbers are misclassified as 8. That's why when we turn all of these to the error matrix and the second matrix that we have, if you scroll down, so that's why those numbers, like the next one, on the next one, right? Yeah, there. So that's why those numbers are more like are bringing, like they're more showing themselves on this matrix. Because we've, so if you see the diagonal line here is dark because we basically took out all that is correct. So all we left is just errors. So these are all the misclassifications. And so the misclassification is mostly on the 8 column and the column is prediction. So lots of numbers have been mispredicted as a number 8. So that's why we are having all those increased intensities in that column. And the rows are the actual numbers.
Okay. You done, Toby?
Yes, I am. That's the end of the chapter.
So first of all, like big kudos to Toby, right?
Yes.
Yeah.
Yeah, I think it was very, very good, very organized. So thank you for that. Now, guys, this is a very, very important chapter. Don't even get so bogged down with the, obviously when I say this, I exclude Toby and Chima because I expect you to be building models, right? But this is a chapter that helps you understand some basic things, right? So if Nazanin next time presents on the confusion matrix, if it's just four things, then you know that this is a binary classification, right? You only have 2 things. But if Nazanin presents some big, many squares and with different colors, then I know, oh, this is a multi-class task, right? Which is why I need to see how the matrix looks like and where it's, you know, either being too bright and changing color and making sure that I'm investigating that, right? We have a little bit of a sense of, you know, the precision, recall, the confusion matrix, how to interpret them, the ROC curve, the area under the ROC curve, because this is how you're going to communicate, right? So when Abby joins in or is reading a paper, or I'm saying, can you look at the results of someone? Then you should be able to look, oh, but the Nazanin falls into the same class as Chim and Toby. But, you know, you can look and be like, oh, this model sucks, right? And you can explain it by this chapter, which I think these are basic fundamentals that we all have to understand, okay? Okay. Who's going to lead? So Toby, did you find a good task? I know Elmira sent me a request to join the housing challenge. Match that. But did you find a good task for people who want to? Ooh, you went for multi-class classification?
Yes, but I could not really find one that is robust.
So the exercise there says the Titanic, right? Like on the book. If you go to the end in the exercises, not that, like in the book, go back to your book, your PDF.
The PDF.
Okay.
If you scroll to exercise.
So, and we'll get some time where we go through all the exercises. Scroll down.
Yeah.
So you can see, tackle the Titanic data set. So click on the cargo. That's pretty sad. It's to create a model that predicts which passengers survived the Titanic shipwreck. It's pretty sad, but so go to evaluation. So the metric is percentage of passengers you correctly predict, right? So this is a binary classification and you're using accuracy, right? That's the ultimate thing. And then look at the data. So this is already split as test and train. Never look at the test set, but train, or you can do the summary, maybe 25. Oh, I think you have to say, I understand and I agree.
Down there in the overview, it gives the description of the, like if you scroll up a bit, there, if you let it out, it tells you where everything, yeah.
All right, so this is a good one to try, right? Simple. Yeah, okay. So do we have any comments, questions, and then we'll talk about next steps? Sina, you've been very quiet. Are you giving up?
No, I'm not giving up. It's the thing that I find really interesting about this whole thing, and I'm understanding it more, the Python is kind of like a spell book, and it has a bunch of curses. You're like, oh, I want to model this. I want to have a matrix. Oh, here's a spell for it. And it's both amazing and frustrating. I was like, how was I supposed to know that existed? But it's pretty cool. What I'm mostly focusing on and trying to kind of get the concept and what they're trying to do, kind of like the specificity sensitivity, that made sense to me, I guess, from the background. But I'm mostly trying to understand how they're doing it. And I'm kind of Googling like what these sets and series and matrices are to kind of learn a little bit of the foundation as well. So I'm kind of going along for the ride here, but I'm not giving up yet.
Good. Okay, Abigail.
I'm also kind of doing the same, just like reading the chapter, try to understand, put it in the collab and see what works. And if it doesn't work, just Google and learn. And it's just catching on slowly, I feel.
Okay. I still encourage you to try still like the Titanic, right? You can just literally modify the code, the source of the data in your collab, and run the same thing and see what you get, right?
Okay.
Okay, Nazanin, did you learn anything new today?
Yes, somehow, but I want to add a comment. It's my personal experiment. Actually, when you want to choose a metric for evaluating your model, you should first look at your data. For example, if you have an imbalanced data set, it is the AUC sometimes doesn't work well. So for example, you can get high AUC, but you will get, for example, F1 score really low. And you have to be careful about this.
Okay. So how can you explain what's an imbalanced data set and how you usually solve it? Because I know you've run quite a number of experiments.
Yes. The imbalanced data set, for example, like here, we have we have more samples for one class, and for example, lower samples for other class, for binary classification. Or if we have multiple classes, we don't have the same samples for each class. So, for example, when we want to, for example, use accuracy for the metric for evaluating our model in this case, as you saw and Toby told, the accuracy is not good because it's really high, because our most of the samples are 5, or maybe our most of the samples are not 5. And if the model randomly tells us predict some samples, we get high accuracy. So the imbalanced data set is when our samples for each class are not equal. For example, for one class, we have a lot of samples. And for handling the imbalance data sets, we have lots of techniques. For example, we can add more images for the generate more images for the class that we doesn't have enough samples, or maybe use undersampling, which means, for example, we equal the samples for each class with undersampling the the class that has high samples, lots of samples. Or maybe, yes, this is one of the techniques I used. Or maybe weighted class is one other samples. We can give a weight for each class that when our model trains, it's, for example, it's C at the low samples with more weight. And in this phase, it trains equally for both the classes.
Okay. So, okay. Next is Chima. Did you learn anything new?
Yes, I did. In terms of the distinction between, I knew which one was it? I knew multi-label, multi-class classification. It was more along the lines of learning that with multi-label, and I didn't know they were different. They were beyond the multi-class. You know?
Okay. Toby, did you learn anything new?
Yes, I did. I learned many things. I learned a lot, having to read and find ways of explaining it.
That's the
So,
bad.
yes.
Okay. Elmira.
Obviously, I learn, like every week, I learn a lot of things. All of them are new, and like all of them are so exciting to me. And one thing about this, as Chima said, I didn't know that there are some models that are only binary. They can just say a class is present or not. This is a 5 or not a 5 when it's trying to like look at numbers. And like I like that. I like the fact that these are so. For example, support vector machine or like stochastic like gradient descent classifiers. These are strictly binary, and there are some other models like algorithms like logistic regression classifiers, like random forest. They can be multi-class classifiers. So, and it's interesting that he went through that when we can use this strictly binary classifiers to look and modify them to just do multi-class, basically using multiple of the binary classifiers to actually serve us as a multi-class classifier. So that's something that I found interesting. I don't know how to, I'm gonna use it, but it's interesting that he presented those that way.
Awesome. Okay, I mean, I thought it was a great recap of the metrics. It's starting to lay the foundation, right? You're starting to think, gee, if Judy tells me to predict a house price, this is a continuous variable. You know, we went through how to deal with integers, objects, get them into categories, use correlation matrix on the last time, figure out what features are important and put those into a model, right? We haven't done this to create a test set, to split the test set, but we know that we always have to do that. And then now all of a sudden we had a classification task. And you know, it shows you that these are more categories, not continuous variables, and what metrics you're using. So at baseline, you should be able to, like, this should be getting to your normal vocabulary. So when you see, oh, Judy's presenting on a chest x-ray, tell us about the chest x-ray data set, and it's presenting pneumonia or non-pneumonia, bam, right? You know that this is a classification task. These are the metrics I want to hear. This is what they mean, okay? And if you're saying, oh, you know, let's figure out what's the creatinine level. You know, it's a regression task. These are the metrics you want to say, right? Or the wisdom task, which is a task I give quite a bit for interviews of students, or something about like the blood glucose level, right? So this is what I want your head to be wrapping around and being like, I know what this means. You know, now I do believe, though, we're gonna start to get into the weeds here. The best thing I really encourage you to go is just spend a little bit of time, especially when you're bored, just organize your notebooks again, or even just go through the notebook again. If you see mine, I keep adding notes into it so that when I have to do a new task, it's not like I'm starting from scratch, you know, and that is super helpful, right? So for example, things you could try out is import a new data set, right? You know, find out, does scikit-learn have the Titanic data set? Can you import it? And then can you run your notebook like that? Experiment, 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 and practice is how you get. It's how absolutely you get better. Okay? Okay. So who's going to be leading us chapter 4? This is building machine learning models, building models. Has a lot of math.
I know, I saw it. I saw it. I have the math behind it.
No volunteers?
Can I volunteer again?
I can try.
Let's give someone else a trial.
I can try. This is my class.
Huh?
The math behind them.
What?
I don't particularly like it. This is what we do in class, the math behind them. But
You don't like it?
I can try it. I can try.
Okay. Toby's at a very high level. I'm not discouraging you. We'll be great. We'll all do it together. Okay. Awesome. Okay, so let's meet next week. Guys, let's use the Slack channel to keep in touch of the week. If you have a, you know, something that's going on, or you find a good resource for people, just put it up there, okay?
Yeah.
Thank you.
Okay, thank you so much.
Thank you. So Judy, are you gonna accept us to the
Yes.
Kaggle thing? All right.
Yes.
Sounds good.
Same as last week. If you have any problem with the code, feel free. Or if you want, you can DM me. We can set up a time too, and we can all just work through it.
Awesome.
Thank you.
Okay,
Thank
bye.
you.